Hello everyone, welcome to my new video in my Mathematics Essentials series. I'm going to continue proving trigonometric identities, and in this video I will prove identities 10 and 11 from our list of 19. Okay, and these are the last identities that I will prove geometrically. After that, the remaining 16 will be proven just by applying identities that we have previously proven. Okay, now it turns out that we only need to give one geometric proof in order to prove both of these identities 10 and 11, and they are called, not the proofs, the identities. The identities are called the sum formula because you are taking the cosine or the sine of the sum of angles. And, for similar reasons, these are called the difference formula. Okay, so I won't prove the difference formula. I'll prove 10 and 11, which are the sum formula. And it's not in this video, I'm going to prove them all eventually. But in the proof, I'm going to make use of the following fact. Okay, in any right angle triangle, any of the non-right angles is just pi over 2 minus the other non-right angle. So for instance, we have this right angle triangle here, and we've called this angle phi. Well, this angle here, okay, this angle is just going to be pi over 2 minus phi. Okay, and to see this, just recall that the interior angles of a right angle triangle must sum to pi radians or 180 degrees. So let's suppose we introduced alpha here to be the other non-right angle in this triangle. Okay, we can just sum the angles. So in this case, we have alpha plus phi plus the other angle, which is a right angle, so that's pi over 2. Okay, that must be equal to pi. All right, now solving for alpha just gets you the following expression. Okay, subtracting pi over 2 and phi from both sides just gets pi minus pi over 2. Okay, minus phi on the right-hand side. Okay, and of course, pi minus pi over 2 is pi over 2. So we are left with this expression that tells us that alpha is equal to pi over 2 minus phi. So we didn't actually have to introduce new notation for this other non-right angle. Okay, we expressed it in terms of phi. Okay, so that's handy because you can express two unknown angles in terms of one unknown angle. And when you're working with equations that involve those angles, you will get like terms. Okay, so let's start the proof. Okay, and I will get rid of this. Okay, so proof of identities. It's 10 and 11. Okay. Now let's just recall what they say. Okay, these are the identities that we're proving. Okay. So we're taking the cosine of theta plus phi, and we're taking the sine of theta plus phi, and you can see what they are equal to on the right-hand sides of those equations. So in this proof, we will actually make use of this right angle triangle, and we have the hypotenuse of this right angle triangle equal to the radius of the unit circle. So this hypotenuse here must be 1, okay? And we'll call this angle here phi. Now, I want you to imagine that we keep this vertice of the triangle fixed at the origin, but we allow the rest of the triangle to move, so we can rotate it around. So for instance, the hypotenuse is sort of tracing out the unit circle as we rotate it. Okay, so let's imagine that we rotate it counterclockwise like this. So we rotate it counterclockwise, and the amount that we rotate it counterclockwise by is an angle that we will call theta. Okay, so don't worry, that's in a diagram. Okay, so we've picked the triangle up, and you can see that this length here is what used to be the x-axis, and this is what used to be the y-axis. We've just rotated this triangle, and this is how much we've rotated it by. Okay, so we can call that angle there theta. Okay, and we inscribe it inside this rectangle. Now, once we inscribe it inside this rectangle, we end up defining 4 right angle triangles in total in the rectangle. So we have this one, okay, this lower one, this upper right one, and this one on the left. Okay, 4 right angle triangles in total. And what we can do is get expressions for the angles in these triangles and the side lengths. Okay, we won't actually need all of the angles. It turns out we won't need this one. Okay, so I won't bother with it. But we will need all of the side lengths. Now, we can already go ahead and write down some angles. We know that this angle must be pi over 2 minus theta, and we know that this angle must be pi over 2 minus phi. Okay, now let's start solving for other angles. Okay, we know that this total angle here must be pi. Okay, so this is similar to our fact about the interior angles of triangles summing to pi radians. We can add this angle to this angle to this angle once, and we can introduce some notation to make that convenient. So we'll just call it alpha. Okay, and summing those 3 angles must equal pi. So let's do that. Well, alpha plus this angle, which is a right angle, so it's just pi over 2. Okay, plus this angle, which we have an expression for, so that's pi over 2 minus theta. Okay, that must all be equal to pi. Okay, so when we simplify this, we just get that alpha plus, well, pi over 2 plus pi over 2 is just pi, and we're subtracting theta, and it's equal to pi. All right, so we can see that subtracting pi from both sides gets 0, so alpha minus theta equals 0, so alpha must be equal to theta. So we can do away with this notation alpha for this angle because we know it's equal to one of the other angles that we have already named, okay, theta. All right, and that means or implies that this angle here is pi over 2 minus theta. So now we can apply the same argument to this angle here in order to find this third one. All right, so if we sum those angles and we introduce, let's say, beta for the third angle, well, beta plus this angle here, pi over 2 minus phi, plus this angle here, which is pi over 2 minus theta, well, they must all sum to pi radians, okay? So pi over 2 plus pi over 2 is pi. Subtracting pi from both sides, okay, we would have pi minus pi on the right-hand side. So in other words, or when we simplify, we have beta equals pi minus pi, okay, and subtracting the other two angles as well from both sides, we have plus theta plus phi. So of course, pi minus pi is 0, so we just have beta equal to theta plus phi. So now we can get rid of this notation beta, and we can write this angle in terms of other angles, which we already have expressions for. So we don't need to introduce any new notation. That's what I'm getting at. So this angle is theta plus phi. Okay. So I did say that we won't need this angle, so let's not bother with it. And now we can turn our attention to finding side lengths. I'll just get rid of all this because it's all captured in the geometry. All of this information is captured by the geometry. So let's turn our attention to side lengths, and we will cover the central triangle first. Now, what we can do is we can take the sine of phi. Okay, now if we take this, or the cosine of phi, let's take the cosine of phi. If we take the cosine of phi, well, that's just adjacent. We don't have an expression for that, so we will just abbreviate the word adjacent over the hypotenuse, but the hypotenuse is 1. Okay, so this is just division by 1, which of course has no effect. So we are left with this equation that says that the cosine of phi is the adjacent side. So I will write that in here. This is the adjacent side, and it has a length equal to the cosine of phi. All right, now if we take the sine of phi, okay, a similar thing happens. It's the opposite side over the hypotenuse. This is the opposite side, and still the hypotenuse is 1, so no need to divide by it. And now we have an expression for the opposite side in this triangle. So I'll write that in here on this angle, that this is this length is equal to the sine of phi. So now we have expressions for all of the angles and all of the side lengths of this central triangle. Let's cover the lower triangle. Okay, so I'll get rid of this so I have some space. Now, if we do this, we can take the cosine of this angle theta. When we take the cosine of theta, well, that's adjacent over hypotenuse. This time the hypotenuse is not 1. Okay, this is the adjacent side. This is the hypotenuse. Okay, and the hypotenuse in this case is the cosine of phi. So it's not 1, but at least we have an expression for it. So multiplying both sides, excuse me, by the cosine of phi, we get that the cosine of theta times the cosine of phi is the length of the adjacent side. So now we can write that in. Okay, and note that in finding the length of the adjacent side of this triangle, this right angle triangle, I'll actually write it outside. I'll write it down here. We've also found the length of the base side of this rectangle. Okay, cosine of theta times the cosine of phi. Okay, so that's the length of the adjacent side of this right angle triangle, but also the length of one of the sides of the rectangle. Okay, so it must also be the length of this top side here. Okay, now let's take the sine. So we take the sine of the angle theta, and we know that that's equal to opposite of hypotenuse. We know that the hypotenuse is the cosine of phi, and when we multiply both sides by the cosine of phi, we get an expression for the opposite side. Okay, so I'll write that in vertically. So hopefully it's not too messy. The sine of theta times the cosine of phi. Okay, so now we have we've finished with this lower triangle. Let's tackle this upper right triangle. I'll just give myself some more some more space. Excuse me, I'm going to take a sip of my coffee. Okay, so now let's take the cosine and the sine of this angle here. Okay, if we take the cosine of the angle theta, well, this is the adjacent side, and this is the hypotenuse. So we have the adjacent side over the hypotenuse, which is the sine of phi. Now, multiplying both sides by the sine of phi, we get that the cosine of theta times the sine of phi as an expression for the adjacent side. Okay, so I'll write that vertically again. Okay, the cosine of theta times the sine of phi. Alrighty, let's take the sine of theta. Take the sine of theta. Well, this would be the opposite side. And again, this is the hypotenuse. So this is just equal to the opposite side over the hypotenuse, which is the sine of phi. Okay. So no surprises, we get this expression that says that the sine of theta times the sine of phi is the length of the opposite side. So hooray for getting to write on a normal angle. Okay, so this here is the sine of theta times the sine of phi. Okay, it's nice not to have to write vertically. or on some funny angle. Now we are done with the upper right triangle. So let's turn our attention to this left triangle, which is going to be quick because the hypotenuse in this triangle is 1. So the cosine of, let's take the cosine and the sine of this angle here. Okay, so the cosine of theta plus phi is equal to the adjacent side of this triangle because the hypotenuse is 1. So let's write that in. This is the adjacent side here. This is the cosine of theta plus phi. And now we just have to take the sine of that angle, okay, which is going to be opposite over hypotenuse, but the hypotenuse is 1. So this is the last time I have to write vertically. Okay, this is the sine of theta plus phi. Okay, now what we know is that the opposite side lengths, the opposite sides of a rectangle must be of equal length. Okay, so we have an expression for the bottom side of the rectangle. Okay, that expression is the cosine of theta times the cosine of phi. Okay, and we have an expression for the top length, and that's basically this expression plus this expression. Okay, so we can set them equal. We're basically saying that the top side equals the bottom side when we do this, or the length of the top side equals the length of the bottom side. Okay, so this is the other expression, or the two expressions that we sum to get the length of the top side of the rectangle. Okay, now what we can do is solve for this. So we have the cosine of theta plus phi equals, well, subtracting the sine of theta from both sides, we just get the cosine of theta times the cosine of phi minus the sine of theta times the sine of phi. And this is trigonometric identity 10, okay, which is trigonometric identity 10. Okay, so we've proven 10. Okay, now if we do the same thing with the left and right sides of the rectangle, so these sides, which we know must also be of equal length, we immediately derive trigonometric identity number 11. Okay, so our expression for the side length, okay, the left side length of the rectangle is the sine of the sum of these angles, theta and phi, and that must be equal to this expression plus this expression. Okay, so that's equal to the sine of theta times the cosine of phi plus the cosine of theta times the sine of phi, which is trigonometric identity 11. Okay, so this completes our proof of both of those trigonometric identities, the sum formula, or the sum formulae, plural. Okay, and both of them fell out of one proof. So we can go up to our list of trigonometric identities and cross two of them out, because it's always nice to cross things off a to-do list. Okay, and I will just go back down to the diagram so that you could pause the video and look at it in case anything wasn't clear, or in case you want to do some reasoning. And if you have any questions about it, you can just post a comment. Okay, so that completes all of the geometric proofs for the three identities that we will prove geometrically. Everything else now is proved by applying identities. And I think I'll leave the video there. So if you enjoyed this video, feel free to give it a like or share. If you have a question, just make a comment. And if you would like a notification when I upload a new video, just subscribe to my channel. Until next time, bye for now.